All right, so it's a pleasure to continue the Nuremberg lecture of the geometric analysis by two lectures by Bernstein. So there will be lectures right now, and the next one, which will be aimed at the general audience tomorrow. So let me say a few words about the speaker. So Professor Bernstein is a leading expert on minimum surface theory and curvature flow. He has received his PhD in 2009 at MIT, and after completing an NSF postdoctoral fellowship at Stanford, followed by a research fellowship at Cambridge, joined in 2012 the Department of Mathematics at Johns Hopkins University, where he's now a professor. So it's a great pleasure.
Thank you for the kind introduction, and thank you to the organizers for the invitation and opportunity to speak here. I haven't been to Montreal in many years. So today I'm going to talk about problems that have to do with another important class of solutions of the mean curvature flow, which are the so-called self-expanding solutions. Let me get started. So maybe to motivate things, we kind of take mean curvature flow for granted. Wu gave a very nice overview, but one of the things you can do with a geometric flow, because it is sort of a heat equation on some level, is try and use it to regularize things. And so maybe the simplest singular thing you might want to try and regularize is a sort of very simple cone. So we're going to start with a regular cone, which is just a closed subset of Euclidean space that is dilation invariant around the origin. And it's regular in the sense that the only singularity is at the origin. So if you remove the origin, you get something that's a hypersurface, and the regularity of that hypersurface may depend on the precise thing you're studying, but smooth is usually interesting enough. Though, as we'll see, there are certain situations where it's helpful to have less regularity. And again, our sort of motivating problem is to understand how the mean curvature flow can be used to sort of smooth out this singular object. And in other words, if you want to study a mean curvature flow that, say, exists for positive time, and sort of as you go back to the initial time zero, you sort of achieve the cone in some sense. So this notion of limit here is sort of, there are various ways you can interpret it, but we'll leave it kind of vague for the moment. And the other thing that will maybe become apparent later in the talk is, right, obviously there's the classical mean curvature flow, which Wu talked about, where everything kind of makes sense classically, but it will also be helpful to allow us to consider things where singularities form after the initial singularity. So we want to also allow sort of weak solutions in various senses. Okay, so that's the motivating problem. And so one of the first sort of things we can try and do is simplify things a bit, and suppose that we sort of know a priori that there is a unique mean curvature flow coming out of the cone. So there's two things here. There's existence. That part is not so hard to believe. I think there's a lot of reasons to believe there should be at least some mean curvature flow. We're also making a much stronger assumption, which is that it's unique, which, as we'll see, is in the context of singular problems, is very strong, and maybe not something you should expect in general. So suppose we have this mean curvature flow G, or which again is sort of coming out of the cone. And the observation is that if we kind of do a parabolic dilation of the flow, which is what's indicated here, this G sub rho, right? This G sub rho, right? So there's a symmetry of the flow, which is that it's I mean, there's translation symmetries or rotation symmetries, but there's also a kind of parabolic dilation, which is here. And this is also a mean curvature flow, and it's because the cone itself is dilation invariant, and it's at time zero, it's sort of it's left invariant by this dilation, and so this is also a mean curvature flow coming out of the cone. And so because we've assumed that there's only one flow, they have to be the same. And that means that G is the same as G rho for all rho, which if you kind of unwind what that means, it means that the time slices of the flow, the gamma t's, are actually just square root of t times gamma 1, right? So the flow is self-similarly expanding. So this is what we would call a self-expander. Right, so we either refer to the flow as the self-expander or the time slice. So Wu mentioned these, but just to keep in mind, these are sort of the forward in time analogs shrinkers, which of course are shrinking down, and sort of model how singularities form. If you like, these are sort of models of how the singularities might smooth, especially if the expander is smooth. Okay, so let's maybe, as I say, we'll see that this uniqueness assumption is very strong. However, there are a kind of large class of interesting cones for which you can prove that it holds. So we at least get a lot of expanders just from kind of, I would say, classical results of mean curvature flow. So if we suppose the cone is graphical, right, so that you can write it as a graph of one homogeneous function, right? So this is just a, you know, I mean, the plane would be an example, but sort of perturbations of the plane that are conical would be good examples. So if you have this sort of graphical cone, then that fits into the framework of a work of Ecker and Huesken about graphical mean curvature flow. And so they had some work in the 80s studying these guys. And one of the things they were able to show is that there is actually a global solution that's smooth and is graphical for all time that should sort of come out of this cone, this graphical cone. And in fact, what they show is that if you take this flow kind of existing forward in time for all time and then parabolically dilate down, you should extract from the estimates they prove a solution that's actually a graphical solution that's also self-expanding. So their result gives you the existence of the expander, and then it's not too hard to see that if you have a graphical self-expander, it has to be the unique one. So you get a uniqueness as well. I should say, if you actually use that as graphical, right, you can translate up and down, and that gives you other solutions that are initially disjoint because the cone is graphical, so upward translation remains disjoint. So you can actually exploit the avoidance property of mean curvature flows to show that actually the graphicality sort of directly implies uniqueness. There's a slight subtlety here, which I don't want to get into, but is important to keep in mind. So typically, the avoidance principle is based on the maximum principle, and so typically it requires one of the surfaces flowing by mean curvature flow to be compact. So the fact that they're both non-compact here is a little bit of a technical issue, but because of the graphicality and there's ways to get around it. It's not, but it definitely adds a little bit of complexity to the problem. Okay, so in the case, to summarize, so if you have a kind of graphical cone, then you get a unique solution, and hence you get the only solution coming out is the self-expander. So we definitely have examples in this case. So with that in mind, maybe rather than this question of how to resolve cones, let's sort of focus on these special solutions, which are the self-expanders, right? So this is in principle, every possible resolution, but as we'll see, there are other ones. But let's focus on them as the simplest for now, right? So again, we have this sort of heat flow characterization of expanders as sort of the solutions of mean curvature flow that expand homothetically. But if we kind of write down the mean curvature flow and use the ansatz of expanding, we see that actually they satisfy this nice geometric PDE of sort of mean curvature type, where the mean curvature vector of the surface is actually the normal part of the position vector divided by 2. Right. So again, this is very similar to the Schrinker equation. There's just a difference of a sign here. But as we'll see, the properties of these two objects are quite different. So the sign is quite important. And again, once we have this equation, we can sort of go back to sort of an observation of Tom Ilmanen, which is that we can realize this equation as sort of the Euler-Lagrange equations of a certain functional. Right, so if we consider this functional E, which is this integral of this extremely rapidly growing weight, so e to the x squared over 4, right? So again, the sign is different than in the case of Schrinkers. Then the critical points of this are also going to be expanders. And again, on a typical non-compact hypersurface, this is always infinite. But the point is the variations are all compactly supported. So this is a typical thing where we can talk about critical points of this functional, even though it's sort of infinite value. And of course, once we have this variational characterization, we get to, first of all, talk about weak notions of expander, and we can also use sort of tools from the calculus of variations to talk about existence. So as I said, right, this is typically infinite on non-compact hypersurfaces, and it's not hard to see there are actually no closed self-expanders. So this is basically always infinite. So you can either see this from the PDE, or it's very easy to see from the avoidance principle of mean curvature flow, right? The expander is moving outward. If it's compact, you can put it inside of a big ball, which is moving inwards, and at some point they'd have to touch. So that's not allowed. So instead of the sort of natural class, which again goes back to the idea of resolving cones, is that we want to look at expanders that are sort of asymptotic to a given cone. So we would call such an expander an asymptotically conical one with asymptotic cone C, which we think of as a function of gamma. And again, the C here is in the framework of the flow point of view. This is the initial data of the expanding flow generated by gamma. Yep.
Why is the function finite?
What about it?
It's finite.
Is it finite?
Yeah.
No, it's never finite.
Yeah. So what do you mean the variation?
Well, the point is the variations are compactly supported, right? So, right, if you what you're really doing is you're taking the variation, which is supported in some big ball, and you're really computing this on the intersection of the sigma with the big ball. So that's finite. But the point is the derivative sort of doesn't care what's happening outside of the supported variation. So, right, this is typical, like, in minimal surface theory, we often talk of, area, there's lots of situations where we can talk about kind of critical points of things that are infinite because the variations are, compact. So that kind of, by the way, so, Lou alluded to this, and I'll maybe briefly mention this. There is a way to kind of sort of, if you like, renormalize this or make this relative by kind of subtracting off the infinity. And then you really can think of this as a critical point of a finite value functional, but that kind of is quite a bit of work. So, but this idea of kind of compactly supported deformations is I think, allows you to avoid this issue of infinite and finite. Okay, so with this variational observation, right? And again, I think Lou mentioned this, but let me just remind you, we can actually show existence for expanders for very, very large class files. So this was a sketch by Hopkins in 5 and a big, so that's what they were details in 2020. But again, suppose we're in dimension where we have a good regularity theory for say area minimizing hypersurfaces, and suppose we have a regular cone of sufficient regularity, so maybe C2. So what can be shown is that for such a cone, there's always at least one self-expander gamma that has the given cone as its asymptotic cone. And in fact, if you allow singular self-expanders, if you're willing to work with a variational or weak notion of solutions of the equation on the previous slide, then in fact, you get a self-expander for every dimension. It just has codimension 7 singular set principle. Okay, and it's just worth mentioning, of course, the way we construct this is sort of by minimizing. And so the thing we produce in the end has to be E minimizing in a local sense, which is to say it's E stable. So it's a special kind of critical point. And again, the basic idea is you sort of intersect the cone with the ball and minimize the E functional with respect to the boundary that you get by intersecting the cone with the boundary of the ball, and then show that you can take a limit, whether you take the radius of the balls to infinity and pass to a subsequence and produce something. And the main difficulty is to show that you get something in the limit, and that thing you get in the limit is actually asymptotic to the original cone. But you can do that with the barrier argument. Okay, so there's lots of cones, lots of expanders. There's certainly lots of cones, but now we also see there's lots of expanders. So the flip side is that there's also, as has been known for a while there's lots of existence, there's a very, very little uniqueness. So this graphical case is sort of not the situation one always gets. So in a general cone, you don't get uniqueness for self-expanders, right? So this goes back to a kind of some numerical work of Angin and Illman and Chop, right? So they take a family of sort of rotationally symmetric cones that have two sheets, right? So it looks kind of like a cross, and then they rotate it around. This will be a picture on the next slide. And they essentially showed that there's a critical angle, so that when you're above that critical angle, you get a unique evolution out of the cone, and hence there's a unique expander. But when you're below this critical angle, there are at least two symmetric expanders. And they're quite different. So one of them is a disconnected expander, right? And the other one is a connected expander. So it's right. So not only do you have non-uniqueness, you can really get non-uniqueness where there are different topological types, one connected, one disconnected. And in fact, so Hellmansdorfer, and recently, he actually showed, unsurprisingly, there's actually another one-sheeted example, so which I call gamma prime theta. Right, so let me maybe show the picture. Right, so here is the here's sort of a cross section. I got this from a paper they wrote, Topping and Hellmansdorfer. Right, so here's the angle theta, and so right when theta is very large, right, this cone is very thin, and you only get these two one-sheeted guys that shoot off on either side, and you can actually produce these essentially by treating the double cone as two single cones, and each single cone is graphical, so you can appeal to the Ecker-Huisken result to produce them separately and then put them together. And it's not hard to see when the cone is too thin. Right? I mean, there are reasons to see that this can't happen, that this is not allowed. Whereas if the cone is if the angle is small, so the cone is very fat, it starts being sort of more optimal to kind of come in like this, and so that's how you get these solutions. Now they actually produced it by just an ODE technique because the symmetry reduces it to an ODE. But okay, so we get, and then the point is there's a third one by Hellmansdorfer, but they look similar qualitatively to the one on the. So that shows that there's definitely non-uniqueness, and there's even really non-uniqueness in this topological. Okay, so another consequence which is worth mentioning, which again I think Lou kind of alluded to, but maybe I'll spend a little more time on, is once you get this non-uniqueness of self-expanders, you also get the existence of non-self-similar evolutions out of a cone. So so really, while self-expanders are the simplest evolution out of a cone, they're not the only ones. So the idea is basically, roughly speaking, is let's say you have two self-expanders, gamma minus and gamma plus, and they're both asymptotic to C, the fixed cone. So it's not implausible that right, these are sort of critical points of this functional E. It's not so implausible that there's something kind of similar to a Morse trajectory kind of connecting the two critical points if the indices work out correctly. So what you might imagine is there's actually a mean curvature flow that exists for all positive time, so that sort of as the time tends to zero, so this is ln of t going to minus infinity, the rescaled flow is giving you is modeled on the gamma minus expander, whereas time goes to infinity, which is ln of t going to plus infinity, the expander is modeled on the plus infinity cone. And so the idea is this is a non-self evolution out of the cone that sort of looks like expanders on either end, but is not itself self-similar. So my PhD student, Lei-Tian Chen, he actually kind of studied this in this setting of rotational symmetry. So he showed that for the theta in between 0 and pi over 2, as long as the cone satisfied some technical condition, which I don't want to get into, but seems is checkable in any given cone and maybe seems superfluous, any mean curvature flow M that's regular enough, again, there's some technical things here, that comes out of the cone is actually rotationally symmetric. So he gets symmetry for the solutions. And as part of kind of understanding what's going on here is he actually shows that there are situations where when you have more than one self-expander, then you actually get non-self-similar flows coming out of the cone, coming from that satisfy exactly this. So maybe going back, the idea is there's one of these solutions here should be unstable, and the unstable one, it should be able to flow towards one of that looks like this that's stable on one side, and then it looks like this that looks like it's unstable on the other side, but you have a neck. So let me maybe say a little bit more about that. Right. So again, the basic idea, which you have to kind of do some work to formalize, is that if you're given an unstable with respect to this E functional self-expander asymptotic to C, then the idea is to try and perturb it in such a way that the perturbed surface kind of moves away from the unstable one and moves towards an E stable limit. So, so this is a very general idea that has been exploited in many different circumstances to great effect. And sort of it's formulated, so my student did it under some conditions related to the previous slide. And then in work in preparation, Lou, he and I are doing a more general construction where if we start with a regular cone and an E unstable expander asymptotic to it, then we can actually produce a non-self-similar solution coming out of it where singularities may be allowed. It may in fact have to occur, as can be seen by examples, and that satisfy the idea that on one side it's going to gamma minus, and on the other side it's going to an E stable gamma plus. And the reason I mention this is, of course, the construction of Illman and Ding can't produce these unstable expanders, right? Because they're only producing stable ones. So it'd be interesting to have other constructions. I should add, just as a remark, it would also be interesting if to try and construct flows that maybe connect different unstable expanders of different indices, but that seems to be quite difficult. Okay, so let's move on to the other methods of finding solutions. So one approach is a kind of a global analysis inspired approach, which is to use a kind of degree theory. So this goes back. I mean, there's several authors it goes back to, but White maybe gave the presentation that we were the most inspired by, where he sort of did this for compact minimal surfaces with boundary, and then later extended it to closed minimal surfaces in manifolds. But inspired by this, right, we show that if you look at the space of all self-expanders where you're also allowing, you're not just fixing the cone, but you're allowing the cone to be a sort of varying parameter, then actually put a sort of manifold structure on that space. And the restriction is we're going to fix an expander. All we're using from that is sort of its top topology. So we're looking at the space of sort of expanders that are parameterized by gamma, right? But the point is that the cones can change, right? It's not that they're just the same kind of on a topological level, but they're not the same cone. So if you look at this whole space, which again, there's a very technical issues with describing it, so I don't want to get into it, but suffice it to say, there's a space of self-expanders of a fixed topological type. They form a sort of Banach manifold, and there's a projection map where you essentially map from the space of expanders to the space of their asymptotic cone. Again, this is maybe the technical point where you actually, on the cone part, you want to kind of keep track of the parameterization, even though you don't want to keep track of the parameterization away from infinity. But I don't want to get into it. But this map is actually smooth and Fredholm and of index 0. Right, so we get this very nice global analysis picture. Maybe I'll have a picture of. Because of this picture, we get immediately some very nice consequences just from kind of standard results about these sort of the existence of these maps. So first of all, we get that if your expander gamma, which is not necessarily this model one, but could be. So if that expander is has no what are called Jacobi fields, so there's no infinitesimal deformations that preserve that are sort of for which the sort of preserve the expander equation. where you column, where you also have to vary the column because each side has a manifold structure. That is not a we feel in the sense that there are none of those guys. That's the only obstruction to this map. Pi being a diffeomorphism, a local diffeomorphism. So you get a nice diffeomorphism in the neighborhood of such a sort of expander with no Jacobi fields. More interestingly, for a sort of generic cone, so for most cones, which we don't know how to check it for a given cone, but for most we know most cones have this property. All the self-expanders asymptotic to it have no such Jacobi fields. So for a generic cone, this map is generically a local diffeomorphism. And finally, when the map is proper, right, which is to say the preimage of a compact set is compact, then it has a well-defined mod 2 degree. And in fact, you can show it has a well-defined integer degree. That's a little more work. So having done all this work, we get some consequences. So we were able to show, among other things, that there was an open set of cones in R3 for which there are unstable expanding annuli. So if you go back to the rotationally symmetric example, Hellmannsdorfer more or less showed that existed in the rotational category, but that's very special. We show it sort of, there's lots of them, like it's sort of a general phenomena. And again, as a consequence, going back to this idea of non-self-similar flows, we get lots of examples of non-self-similar flows out of cones that instantaneously disconnect. So that's sort of a nice consequence about properties. And here's maybe just I think it's hard to understand the theorem, but maybe this helps explain it. So this is sort of, down here, this is sort of the space of cones. Up here is the space of maybe all possible hypersurfaces asymptotic to the cone. And these curves in here are the self-expanders. And so here, C would be, say, a generic cone where they have these 3 expanders lying over it. But you notice that sort of the projection is sort of isomorphism in a neighborhood. So this is a generic case. In the non-generic case, right, we see that we still, in this picture, we have 3 cones, but it's not a local diffeomorphism anymore. And in fact, there's no reason this needs to be there. It could be moved over a little bit, and then you would see only 2 cones. But the point is, if you count things with mod 2, only at the regular, the sort of generic points, you do get 1. So this is a way of seeing that there always is, say, 1 expander of a given topological type if it has this degree. Okay, so that's the global analysis point of view. And I've labeled these with G and L, and there's some arrows here, and maybe that will come back to this picture to make sense of this in a little bit. Okay, so there's another construction to get unstable expanders. But it's helpful to before we do that, to sort of introduce a sort of a natural partial order that exists on the space of expanders asymptotic to a given cone. Right, so in principle, that space could just be a single point, but it could be quite complicated also. So let's fix our cone C and let E of C be the space of all self-expanders asymptotic to it. So again, it could be a point if it was a graphical cone, but it could also be many points or even some kind of continuum in some cases. And we're going to put a partial order on it, which is sort of uniquely determined up to a choice of orientation by saying that, say, gamma 2 is bigger than gamma 1 if and only if gamma 2 lies above gamma 1 in a kind of geometric sense, which maybe I'll have a picture of shortly. So using a kind of modified version of the Illman and Ding result, right? So they have a minimization argument to reduce expanders. Once we're given expanders, we can kind of use them as barriers in the minimization procedure. So it follows from that argument that, in fact, again, this dimension restriction is just for regularity issues, but in fact, there is sort of a unique greatest and least element of this. So it's a partially ordered set, but it has a unique greatest and least element, possibly the same element, but certainly possibly distinct. But in general, there may be 2 elements that are not comparable. It's just a partial order. It's not a total order. But the argument that we use to prove this actually always gives a kind of expander above and below. So maybe, hopefully, this kind of illustrates the idea, right? So So we have this hypersurface, so there's a side of hypersurface, and right, there's two possible choices of side, but the cone, once we orient it appropriately, there's always a unique choice of side. So we just choose the same side for both expanders. And basically, gamma 2 lies above gamma 1 if the set it bounds contains a set gamma 1 bound. Right, so this is gamma 2 bigger than gamma 1. But of course, we can have examples where they're not comparable. So which would be that picture. Of course, in this case, when they're not comparable, there's a kind of singularity here, and we can kind of minimize over here, right? And it can't be either of the two. So it has to be a third one. And that's how we prove that given 2, there's always a third one bigger than both of them, or likewise smaller than both of them. So that's sort of the rough idea. And maybe going back to this picture, right? Again, this is very crude, but we can kind of think of the partial order in this picture as sort of here's the least element, here's the greatest element, here's the middle element, right? Now it's more complicated because maybe this is a very schematic picture, maybe it's coming out of the board, and maybe there's another element out here that's not comparable, but it's always between these two. Okay, so that's the partial order. And so then kind of using this partial order, right, we are able to use, prove a kind of mountain pass result for this E functional. Right, so what it says is that, again, if we're in the dimension where we have nice regularity and we have a nice cone C, if we're sort of given two distinct strictly E-stable expanders, so strictly E-stable just means there's no Jacobi fields, but it's E-stable. So, right, so for example, if the cone was generic, then these are just stable. We don't need the strict here, it's automatic. Right, so if we're given these two expanders and they're ordered, so gamma 1 is below gamma 3, so right, and they're distinct, so there's really some room between them, then we can prove that there's actually a third self-expander that's not equal to either of the two that lies in between the two. So we can find one in the middle. And the point is, if C is a generic cone, so right, then we can further be assured that this gamma 2 we found is actually unstable, which is sort of what you expect from a mountain pass, right? So there's this, you have gamma 1 and gamma 2 are both in the valley, but they're in different valleys. So you want to go over a mountain range to get from gamma 1 and gamma 3, you want to go over a mountain range to get from gamma 3. And the gamma 2 is in principle sitting in the lowest point of the pass between them. And hence it's also unstable. I don't want to get into this, but maybe one of the novelties of our proof here is in the Illman and Ding construction, they do it by using standard techniques of minimizing on compact sets and then taking an exhaustion. So it's conceivably possible you could do that for this here. The difficulty would be that in the compact set, you might produce a third distinct expander, but then in the limit, you don't know if it converges to one of the two on either side. So it requires some delicacy. We sort of sidestep that by not working with compact things, but actually working directly with this relative functional. So we're actually able to do the min-max theory with a finite value functional, even though the E is infinite, but by subtracting off in this nice way, we get something finite. So again, I don't want to get into that, but this is the thing we discussed in the first talk. Okay, so we do get these many unstable self-expanders. So there's a lot of applications of this result, not all of which I can discuss, but one of the things that's worth mentioning is that it immediately shows that at least in low dimensions, right, you can always, okay, this is not quite correct, but okay, so at least there's an open set of cones so that the generic set cones in that open set have E unstable element. But a consequence of that is that there are non-self-similar flows coming out of any cone in the set. So this is not quite correctly stated, but so the point is, in the generic ones, the generic cones in the set, we can get the unstable element and get the interesting flow. But once you have the interesting non-self-similar flow, you can sort of do an approximation to see that it also exists for other cones in the set. So in fact, this E unstable existence is required generic, but the existence of the flow line is true without that assumption. But what this means, and maybe it's worth, this is not really required as a result, but maybe it's worth mentioning here, is that right, the idea of these non-unique evolutions, which you would have here, is that the flow of the mean curvature flow fattens in a certain sense, which again Lou mentioned. Right, so that somehow there are many solutions that you come out of the fixed initial data. Right, one of the things I think she mentioned was that in the context of if your hypersurface is embedded in a foliation, then sort of a generic leaf of the foliation, the flow doesn't fatten. Whereas here, right, these cones, I mean, a good example would be these double cones where you kind of vary the two links separately, right? That gives you a family that is not embedded in a foliation, and generically, and in fact, all of those guys are fattening. So it's sort of right. You don't want to get misled by this result for being embedded in a foliation. I mean, it can be in this non-compact world, and especially in this cone world, it's quite common to see non-uniqueness. So the upshot is that sort of there's some subtleties about these sort of model flows having non-uniqueness, even though maybe uniqueness is more typical in a fixed flow. Okay, so maybe briefly mind the audience has been seen previous talks, and will also be the main topic of the final talk. But let me just remind you, so the holding minimum entropy of a hypersurface is defined to be the supremum of the integral over the hypersurface of this certain heat kernel-like term. Okay, right. And one of the basic properties that I think hopefully you take away anything from this lecture series is that this is an interesting quantity, and it's particularly interesting because it's monotone, non-increasing along the mean curvature flow. So one of the upshots of that is that right, if you have a flow coming out of a cone, then of course the entropy of the surfaces in the flow is controlled by the entropy of the initial object, which is the entropy of the cone, right? Now, on the other hand, the entropy is invariant under dilation. So, right, at least if the MT is an expander, all of these are the same. This is independent of T. Now, that doesn't quite prove that the entropy of gamma is the same as the entropy of the cone, but it's suggestive that it is. And in fact, we can't prove that for reasonable cones, you have equality here. So the entropy, you know, just knowing the entropy of the asymptotic cone controls the entropy of the self-expander, and actually gives you the exact value, which is important. So one of the things we sort of wanted to understand is maybe you have non-uniqueness, which has really caused a lot of problems for applications. But maybe in general you have this non-uniqueness. But maybe if the cone is somehow simple enough, right? Right. So certainly in the graphical case, which seems quite simple, we know we have uniqueness. Maybe if it's simple enough in some other sense, maybe measured by entropy, we can get uniqueness, or maybe something close to uniqueness that might be good enough. So this is actually what we were able to show, right? So we were able to show in recently, it came out, I think it was finished before the pandemic, but has finally appeared in publication. So I'm using publication dates for most of these. So if you have a low dimensions and you have a regular cone, and you have a situation where you have two expanders asymptotic to that cone, with the entropy of cone being sufficiently small, right? So there's definitely lots of cones in this range, right? I mean, the entropy of the plane is 1, so certainly you can perturb that cone to get entropy as close to 1 as you like, and this is around 1.4 or something. So there's a big range here. then all of the two cones have to be topologically equivalent. So this example way back with the right, maybe I'll go back. So here, this is an example, right? This is disconnected and that's connected. So these are not topologically equivalent. So the consequence is that the cones for which these things exist must have entropy that's bigger than the bound we get. Okay, so in that case, they're topologically equivalent. And again, I don't want to maybe say exactly what this means, but it's in our proof, it's actually in the sense that they're isotopic to one another. But certainly, any notion of equivalent is implied by isotopic. It's like probably the strongest notion of equivalent one can prove. And so the reason I mention this is this has a lot of very interesting consequences and maybe far-reaching ones, the ones I'm maybe not ready to talk about yet. But one thing it does imply is this a kind of version, if you like, of the Schoenflies conjecture, at least in the low entropy settings. So, right, so what we can use this to prove, and what kind of inspired us to look at this, is that maybe if you have a closed hypersurface in R4 of sufficiently low entropy, we had earlier proved that it had to be diffeomorphic to the 3-sphere, but it was a question of whether it was isotopic to the 3-sphere. So, right, obviously that would be implied by the Schoenflies conjecture, but it's still a conjecture, but we were able to prove using this that it actually is isotopic. So, okay, so that's the result. And maybe let me try and very briefly sketch the idea of the proof. Okay, so we're going to first start with a very simplified situation, which kind of has the core of the idea, which is we're going to assume that the and let's also assume they're distinct, because of course if they're not distinct, well, it's not interesting. We're done. So we have these two. These are the only two expanders. And let's further assume that the cone is generic. Not only are they stable, but they're actually completely stable.
Okay,
right?
perfect. So we have everything.
So
maybe
because of that, we can immediately appeal to our result from mountain pass group and say that there has to be a third unstable expander, gamma u, that lies in between the two. Okay, so we have these three expanders satisfying this partial order, and none of them are equal to each other. Now, the basic idea, and we, it's the idea is when we constructed these non-self-similar flows, I didn't go into the details, but you're essentially perturbing on either side by the lowest eigenfunction of a certain operator related to the second variation. So you actually have two, given an unstable one that's two-sided, there's always two flows that come out of it that are non-self-similar on either side of it, at least. So we actually have these two flows come out of it from either side. And basically, we know they have to flow to something stable, and we only have two possible stable choices. So one of them flows to gamma L, and the other one has to flow to gamma G, right? There has to be these two directions. And coming out of the cone, so they all have controlled entropy. So the entropy of all of these flows is bounded by this, right? The point is that, and I didn't maybe state this, but it's worth, maybe I'll just say it in words. The flows have an additional property, which is that they're moving in one direction in some sense. And that's a very important property that's it sort of really restricts the kinds of singularities that can form. So it's essentially the same as what happens when you have a mean convex mean curvature flow. And it's been known for a long time that a mean convex mean curvature flow can only form cylindrical or generic singularities. So because of the way the construction works, these have a similar property where you can say exactly the kinds of singularities that can happen. And the point is the entropy assumption prevents any of these singularities from occurring. And so the flow that we construct, these sort of non-self-similar flows, actually, never have singularities. They're classical flows. And so they connect gamma u to gamma L on one side, gamma G on the other side. And since they never form singularities, they're all topologically equivalent. And in a very strong sense, because it's provided by the flow. Right, and maybe this is where this picture is not really correct, but you can kind of see in this idea. So let's look at this generic case. So here's gamma L and here's gamma G, and there's sort of like these flow lines that kind of go out from them, right? That's sort of the picture you have in mind. Okay, and so then, well, what if other expanders in the set? So let's say the other expander, gamma prime, that is accounted for in this list. The point is, since if it's not in the list, it's not stable because we've already accounted for all the stable ones, and hence it has to lie between gamma L and gamma G. Now it might be incomparable to gamma U, we don't know, but the point is it is unstable and lies in between them, and so we can do the same trick with the, the only reason we needed one to get the result. We needed one unstable one, but once we have one unstable one, the same argument applies to all of them, and so we see that this unstable guy is also equivalent to all three of them. And so we see that every expander in this set is topologically equivalent. And of course, the question is, what happens when there are more stable self-expanders? Well, reduction. So used to this situation, right? I mean, there's at least in the generic case, there's only a finite number of the stable ones, and you can kind of reduced to the case where one is right directly on top of another one, and there's no stable one in between, and the same argument kind of works. And then you induct in this sense. And then finally, the non-generic case, right? It's true for generic cone, non-generic cone by the sequence. The approximation is, this is a robust statement under approximation. Get it in the generic case as well. Okay, so maybe the final remark, just to maybe interest people, but I won't say a lot, right? So there's a kind of observation that self-shrinkers are very similar to minimal surfaces. There's also an observation that self-expanders are very similar to minimal surfaces in hyperbolic space. So one thing one would like to do is maybe take this result I said before and see if there's an analogous result in hyperbolic space. So recently, I was able to introduce a notion of entropy in hyperbolic space, where you use the heat of hyperbolic space in a directly analogous way. And it has all the same properties you would like. So we get a notion of entropy in hyperbolic space, which I call lambda h. One of the properties of it is that just as to sort of make this dictionary a little more complete, right? You have the ideal boundary, right, which you can think of as sort of, it doesn't have a Riemannian structure, but it has a kind of conformal structure. So if you take a minimal submanifold that's sort of asymptotic to the ideal boundary, in the sense that there's a kind of a curve on the ideal boundary, then you can define, you can see that this hyperbolic entropy is the same. Okay, sorry, this is there's some factor, right? This isn't correct. There's a normalizing constant. This is a typo constant. So up to some multiplicative constant, the entropy of sigma is the same as the conformal volume of the boundary curve, which is well defined because it's a conformal manifold. So you can't define the length of the area of the boundary. Basically, the volume of all the spherical metric. So my PhD student, Yao, he sort of took what we did, and he was able to prove the analogous results for minimal surfaces in S3. So let's just tackle issues in higher dimensions, but at least in dimension 3, it's very clear. So if you start with the infinity of hyperbolic space, and the boundary entropy is less than the entropy of the conformal volume is less than the entropy of the cylinder. Again, I think there's probably some multiplicative factor I forgot. Then if you have sigma 1 and sigma 2 are two minimal surfaces in H3, both asymptotic sigma, then they have to be topological. So I think that's kind of we get something about. Okay, I'll stop here.
Let me maybe ask a couple of questions. So first of all, this entropy bound that you have, is it, do you expect it to be sharp, like this entropy of the n-1 times r?
Yeah, I mean, I think it's very close to sharp. So if you go to this example, I mean, I mean, it's hard. We did some numerical things with this, but it's hard to quite get this. So if you take these examples, right, this is a good example where you get non-uniqueness. So it's not too hard to see that when the cone is very, very fat, the entropy of the cone should be about 2, because it's kind of like 2 planes, right? So when theta is very close to 0, and then as theta goes to 0, sorry, when theta is 0, it's very fat, so it's 2 planes. But as theta goes to pi over 2, they become very thin cones. And it's not so hard to imagine that as you kind of, the point where the f functional is maximized is taken by translating the cone out. And sort of in the limit, you end up with a cylinder somehow as the angle goes to pi over 2. So as the angle goes to pi over 2, these should give you the entropy of the cylinder. So it seems that the entropy of these double cones should lie between 2 and the entropy of the cylinder. Now, I think numerically it does some weird thing where it actually goes below the entropy of the cylinder briefly from my memory. But the point is these definitely are giving you counterexamples, and the entropy of these is below 2 and just a little bit above the cylinder. So, I mean, it's very hard to get much of an improvement just based off these examples.
A bit of a naive question. So the terminology entropy, so what is the rationale behind it?
Well, I think the rationale is that it's a sexy name, but no, I think
but what does it measure? Sort of?
I think the idea is that it's measuring some. I think the real reason is just it's monotone under mean curvature flow. That's why they called it that. I think some of our work maybe has elucidated that it really is measuring some kind of sense of complexity and sort of how far, at least on some level, something is from being very symmetric. Mm-hmm. But I mean, it certainly has a lot of properties you would want entropy to have. And it certainly seems to be the kind of mean curvature flow analog of the entropy Perelman introduced. But I don't know, that's maybe, you got to ask, Colby and Nicosi.
Okay, thanks. So other questions?
The function E, in general, of course, function E is definitely not bounded finite.
Yeah.
Then you do certain variation with compact support the case. It's possible you can define index for this function.
Yeah, I mean, it's the same basic idea. So the index is you sort of intersect everything. You look in a big ball, raise R, and you compute the index there with Dirichlet boundary data. So that has a well-defined index everyone understands. And then you can sort of use the domain monotonicity to kind of take a limit and say that's the index.
Okay.
Or alternatively, right, you can just it's sort of the it's the max. There's a the second variation formula, and it's the sort of it's the maximal dimension of the subspaces of a space of compactly supported test functions on which the second variation quadratic form is a negative definite away from the origin. So there's definitely a well-defined notion of index, even though it's not.
So in general, the index can be computed.
It can be defined. I don't know if it can be computed so easily, but it can definitely be defined.
So because suppose you have two solutions which are stable, then you produce the other one unstable. Suppose you do have index can be defined, then that's probably lead to the mountain path.
Yeah. Yeah, I think there's definitely, I'm not as much of an expert on the min-max theory as I should be, but there seems to be a lot of results about, I think it's not so unreasonable that the solution we produce is index 1, but and it may even be that if you look at the literature in min-max theory and kind of apply it to our setting, you would be able to deduce that, but I'm not confident about that. But that seems the way these sort of it's a one parameter sweep out that we use to produce it, and the general expectation is that should produce something of index 1.
And then going back to the relative, going to back to the relative energy. Is this energy finite?
Yeah, that was sort of
subtract one of the energy from the cone case, right?
Yeah, so it's not the energy of the cone. Now, the decay rate to the cone. So this is like Wu mentioned. The decay of the expander to the cone is like 1 over the radius, which is not fast enough to compensate for the weight. But if you take 2 expanders, then they decay to each other super exponentially fast. with exactly the right decay rate so that so basically you have to subtract a reference expander, the energy of a reference expander from your given expander to get the relative energy, and that's finite.
And this is finite.
Yeah, and one of the things we observed was, right, and this goes back to this greatest and least element, is if you actually, you have these two expanders and you have this region sort of between them, the greatest and least one. So any hypersurface line in between them, asymptotic to the cone, the relative entropy is well defined. It may be infinite, but it's not negative infinite. So it's so you can sort of restrict to the finite energy ones in there and sort of say useful things about them. That's sort of roughly how we sort of do this proof.
One last question. Going back to in the last slide, or the second to the last, because you define the entropy in the hyperbolic space. Right?
Yeah, this one.
Yeah. You mentioned this conformal volume. That's because more or less that's the volume of sigma. That because you can identify boundary of conformal space as SA, right?
Yeah. So it's I like to think of it in the Poincare ball model.
Right.
So your minimal surface in hyperbolic space in the Poincare ball model, it sort of extends to the boundary of the ball, which is, and it meets it orthogonally. So the sigma is sort of the boundary curve on this boundary of the sphere. But the point is there's, the Poincare ball model, there's if you like, the isometries of hyperbolic space are the, Mobius transformations.
Mm-hmm.
And so you don't get a unique notion of boundary. On the sphere, you only get unique up to action of the Mobius transformations. Mm-hmm. So it doesn't have a unique length, say, but it has a unique, if you take the supremum of all lengths under the action of the Mobius group, that is well defined. And that's essentially what this lambda C is.
Okay.
So
in this case, of course, HN plus one may not necessarily be special. In general, you can do that for any conformally compact.
Possibly, though, I guess the formula we get is very special to hyperbolic space. There's maybe some more you can do, but I don't maybe want to talk about right now. But yeah, there is definitely some. I don't think this is like the end of the story, but maybe the beginning of one. So,
any other questions? Not, let's thank the speaker again.